NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey everybody, welcome to our monthly series of public talks and discussions from NASA's Jet Propulsion Laboratory here in California. I'm Preston Dyches. Well, this month we are super excited because we are getting ready for an epic journey to the Red Planet. So buckle up because we're going to Mars. Now for this show, we have two speakers to share how they're helping to make NASA's next Mars Rover mission a reality. Now, if you're watching live on YouTube or Facebook, you can submit questions via the chat, and we'll work in some of those questions into the show as we go. And so to help us with that, I am really grateful to have my colleague from the NASA Mars Public Engagement team, Sarah Marcotte. Hey, Sarah.
Hey there, Preston. So it's going to be my role to take those questions from YouTube and Facebook, so keep them coming. If you happen to lose the chat window, just refresh your browser and it should appear again.
All right. Thanks, Sarah. I'm glad to have your help. So a quick program note that we found just in the pre-show checkout for our AV that we were having a little trouble with the internet connectivity for our first speaker. So we'll hope for the best there and roll with that. And we hope you'll just hang in there with us as we work through that. But hopefully everything will be fine. Well, NASA's Mars 2020 mission is targeting a launch date of July 20th from Cape Canaveral in Florida. And on board that Atlas V rocket will be the Perseverance Rover. It's the latest in NASA's line of robotic explorers to rove the Red Planet, extending our senses and our presence to the surface of Mars. And so, Sarah, your team is working on a bunch of ways for people to follow along with the mission, both in the run-up to launch and on the journey to Mars. So tell us what you've been up to.
Sure. So I wanted to tell everyone where our one-stop shop for resources to watch this launch will be. It's our website, which is mars.nasa.gov/Mars 2020. Now, that is where everything you need to watch this launch will be located. Now, on this website, we have a page called our Launch Toolkit. And it's just that. It is a toolkit that gives you all the tools you need to watch the launch, whether you can actually join us at Kennedy Space Center in Florida, or you'll be watching online like I will. Now, I do want to mention that in the next few weeks leading up to launch, we're going to be releasing several new experiences. So it's pretty important to check our social channels and to check the website again as we release things in the weeks leading up to our July 20 launch.
All right. Well, thanks a lot, Sarah. That sounds great. So just remember to follow @NASA on Twitter and Facebook. So it is always an exciting time when we head off to Mars with a new mission. And over the years, we've built up some experience in landing and operating spacecraft on the Red Planet, but it's really complicated, really hard. And it takes a lot of people to working together to make it happen. So now in the run-up to launch, we tend to place a lot of focus on the engineering side of things for obvious reasons. But of course, there's also a large team of scientists involved from the beginning who really help to shape what the mission becomes. Everything from what science questions will the rover investigate to where should we land? And so our first speaker is one of those scientists on the Mars 2020 mission. Dr. Briony Horgan is a co-investigator on the rover's camera team and a professor at Purdue University in Indiana. So, hey, Briony.
Hey, how's it going? I'm so happy to be here.
Great. Thanks so much. So now you're a planetary scientist, right? First of all, what does that mean, and how do you describe your job?
So a scientist uses basically any kind of science you can imagine, everything from biology to chemistry to geology, physics, to study the planets in our solar system, to try to understand their history, everything from, what kind, did they ever support life? Or, really, it's a pretty fun job because we get to do a lot. But yeah, so what I to do personally is I actually do planetary geology. So I use mostly images and other data from satellites in orbit around planets, as well as rovers on the ground, to try to understand the past geology of planets like Mars and the Moon, and also back here on Earth, working in the field in the lab.
Cool. And how did you come to be part of the Mars 2020 mission? How does one come to be a Mars rover scientist?
Well, the way we got it was going to send this rover to Mars. JPL is going to build it. Now we're going to reach out to the science community to compete for instruments that are going to go on board. And so back in 2014, I believe, we had a competitive grant competition, basically, where we all the scientists got together and, split up into teams and developed instruments that would help address the big science questions that we wanted to answer with this rover, proposed those instruments, and then NASA selected the ones they thought would be the best for answering those questions. And so I was lucky enough to be on the camera team that was proposed, and we were selected, and now we're going to Mars, and we're really excited.
Awesome. Well, tell us about the Perseverance Rover. I mean, what are the key things that people need to know about this particular rover?
So this rover is what I like to call a robotic astrobiologist. So this rover, the whole goal of the mission is to try to look for signs of ancient life on Mars. Now that's a really big deal. You might have heard a lot in the media about, looking for water on Mars and finding water on Mars. And that's what we've been doing for a long time. We've been trying to understand, what was ancient Mars like? Was it ever Earth-like? So it's really been this big buildup all the way from the Pathfinder rover back in the 90s, to the Spirit and Opportunity rovers back in the early 2000s. Those were our first sort of robot geologists that landed on Mars, trying to look for signs of that ancient water. Was Mars ever Earth-like? And then that was followed up by the Curiosity rover, which is still roving Mars today, in Gale Crater, which was trying to understand whether or not Mars, those watery ancient environments on Mars, could have actually supported life if they were habitable environments. Now that we've done all of that, the rovers, and we've also had satellites in orbit around Mars, trying to understand what the history was like, because looking for little green men running around, we're looking for signs of ancient microbes that might have once lived on Mars. And it turns out it's really, really tough to find signs of microbial life in the geologic record. It's even hard here on Earth. But we think we know enough now that we have a really great landing site that we can go to look for these ancient signs of life. If you bring up graphic 1, you can see a shot of what Mars 2020 we think will look like on the ground. It's artist rendition, the rover investigating some rocks on Mars. This is what we're going to be doing. We'll be roving around the site we'll talk about a little later, Jezero Crater, trying to understand the geologic history of the site, as well as looking for these what we call biosignatures. If you go to graphic 2, so here's where the rover was until recently. This is actually what we call the high bay JPL. It's where the rover was assembled. And you can see this photo is actually of the rover taking its baby steps back in December of last year. Now it's been shipped off to the Cape, and it's getting ready to get loaded onto the rocket, which is really exciting. If you go to graphic 3, you can see some of the really great instruments that are on board the rover. Because really, the rover itself, it's this amazing chassis, this amazing robot that's going to do all this great work. But it's the instruments that really are what the rover is about. And this rover really is an astrobiologist. We have all kinds of amazing instruments on board that are going to be doing things like looking for traces of organics at the millimeter or sub-millimeter scale. We're going to be looking for evidence of, textural biosignatures, all kinds of interesting things like that with our really heavy-duty kind of microscopic payload. A lot of the microscopes you can see are actually out on the end of that 7-foot-long arm. And just for reference, that arm is 7 feet long, and then the turret and all that stuff on the end weighs about as much as a lawnmower. And we're able to place it with sub-millimeter precision, which is really incredible. But that's really the workhorse of this rover is the instruments out on the arm, which are these amazing microscopic instruments that can map organics and minerals and chemistry at this very fine scale that will help us look for science. This rover looked like Mars Rover. You can see just how similar they really are. I mean, they basically have the same chassis. They have the same kind of overall design, but they are very different. You know, the Curiosity rover is basically a roving geology laboratory. It has an incredible suite of instruments that are designed to look at the chemistry of the rocks, the mineralogy of the rocks, because that's where the signs of that ancient habitable environment are trapped, is within the kind of details of the things that make up the rocks. Whereas again, with Mars 2020, we're really looking for signs of ancient biology, and so it has a very different suite of instruments. Even though they look really similar, they're going to be doing really different things on the ground.
Gotcha. Well, it is a remarkable looking piece of machinery. I think it's a good time for us to go to Sarah for our first question from the audience. Sarah, what do you got for Briony?
Sure. Well, I saw some questions come in and they were related very nicely to what Briony was talking about. So Tan on Facebook asks, how are Perseverance's duties, so what it's going to do on the surface of Mars, different from Curiosity? You talked a little bit about how the rovers look very similar, but how are the tasks different when Perseverance gets to Mars?
That's a great question. And actually, it's a great opportunity to talk about sample caching, because that's one of the big things that this rover is going to do, is not just do this great science investigation on the ground with the rocks that are there. We're also going to be selecting samples that we're going to eventually bring back to Earth. And so the way that's going to work, we'll be selecting these kind of pencil-sized drill samples of rock that the rover will doing a lot of the kind of mineral chemistry and trying to rocks are made of. But what's really exciting with 2020, we're actually going to be sampling those rocks to bring back to Earth to look at in our labs back here on Earth. And the reason we're doing that is because if we really want to know whether or not there are signs of life trapped in those rocks, we have to look at them with extremely, just the best instrumentation possible, the best, electron microscopes and things that we have back here on Earth to try to figure that out. It's really hard to do that kind of work, as well as we would like to confirm whether or not there was ever ancient life there on Mars with the rover. And so that's the next step. And so we're going to be collecting those samples. And then later, there's going to be a series of missions that will help bring those samples back to Earth. It's a pretty tough job. Because not only, so 2020 Perseverance Rover is going to be collecting the samples and, documenting them, and will help us decide which ones to bring back. But then we have to land another rover on the ground that'll go get those samples. It'll have to bring those samples back to a launch platform. It'll have to load those samples into a rocket, which will then lift off the launch platform, blast into orbit, rendezvous with a satellite that'll pick up the samples, and then eventually make it back to Earth and land on Earth. So it's really, really tough. It's a lot of steps we have to go through, but we're starting to work on it. NASA and the European Space Agency have actually already started working on this and putting money toward this and developing joint set of missions that'll make this happen. And so we're really excited that, not only are we doing this great astrobiology on the ground with the rover, we're also going to be helping bring back some of the most exciting samples we've ever returned from space.
So, Briony, you've mentioned a word a couple of times that I wanted to ask you to delve into a little bit more deeply. You mentioned biosignatures. So what are biosignatures, and how can they help you understand today whether Mars had life 3 or 4 billion years ago?
It's a great question. So if you go to graphic 5, we have some nicely what these things are. So biosignatures are being left in, I think, could be due to life. And so there's a lot of different things that could be. It could be things like, chemical signatures. Isotopes are a really common one. Life gets in there and really messes with, the different kinds of chemicals that are left behind. It could be, nice, really obvious things like in that middle left, that's what we call a stromatolite. That's a nice textural biosignature that was created by microbial mats on the shores of an ancient lake that kind of helped cement these minerals together and create this really kind of, it looks alive, right? This kind of lifelike texture. It could be a lot of different things. Microfossils are a great example. Even things like a dinosaur bone is technically a biosignature. So, but the difference is, we would love to find a dinosaur bone on Mars, but of course what we're really looking for are these microbial biosignatures. And so that's why, even though, we're going to do as much as we can to characterize organics and textures and all of these things that we think could help us indicate where biosignatures could be on Mars, ultimately we'll have to bring these samples back to Earth to confirm whether or not that's true. So even if we find, say, that amazing rock on the left of the stromatolite, which we hope we might find in our landing site, that would be great. We still have to bring it back to Earth to confirm whether or not that was actually created by microbes.
Wow. And before we go too much farther, Sarah, I wanted to ask you, to mention this, that Perseverance has a helicopter too, right?
Yes, it does, indeedy. It's got a helicopter riding on the belly of the Perseverance Rover. The helicopter's name is Ingenuity, and in the first few weeks or months of the surface operations of Perseverance, so we're talking sometime in the spring of 2021, that helicopter, Ingenuity, may demonstrate the first powered flight on another planet. How cool is that?
That is super cool. And so I wanted to mention the helicopter because I think a lot of people are becoming aware that there's a there's a helicopter on this thing going with this thing. But Briony, does that play into the science of the mission?
We're hoping, yeah. I mean, so the helicopter, it's a technology demonstration. So the basic thing it has to do is show that we, like Sarah said, that we can actually operate powered flight on Mars, that we can operate a helicopter on Mars. But we're hoping, the helicopter has cameras on board, and we're really hoping, what this helicopter and future missions like this will do is help kind of bridge the gap between our, really incredible images we have from satellites in orbit, what we can see from the rover on the ground. Just like drones here on Earth kind of help you get context where you are. They're great for mapping, or great for doing geology and science too. We're hoping the helicopter Ingenuity will help us with that in our landing site. Will help us kind of understand context where the rover is, help us make really cool 3D maps of where we are, all kinds of great like that.
Well, you gave me a perfect bridge to my next question, because you work on the team that is going to take all the incredible images of Mars with Perseverance. So tell us about the cameras. How will they be similar to or different from Curiosity?
Yeah, so I'm on the Mastcam Z team, so that stands for Mast Camera Zoom. And so we had mast cams on Curiosity, and they worked really well. It's really, almost all of the really beautiful color and big mosaics and things that you see from the Curiosity rover, those are almost all taken by the Mastcam cameras. And so we're going to send something fairly similar to Mars. Mastcam Z is pretty similar to Mastcam, except for we have better zoom capabilities. With Mastcam, we actually had the eyes were one was stuck zoomed in, one was stuck zoomed out on purpose to keep things simple. We have the ability to zoom them independently now, which is going to be really great. We're going to have beautiful, 3D mosaics we can make with the two eyes. We're going to be able to, what I actually work on is mineralogy. We can actually do some really simple spectroscopy, looking at the wavelength dependence of light coming off of rocks to help identify their mineral fingerprints. We're going to be able to do that, look at the beautiful colors and all of that with these cameras. They're really kind of the geology workhorses of the mission.
Wow, can't wait
and
to
actually,
see what it shows
we
us.
have a really nice graphic. Oh yeah, sorry. We have a great, if you go to graphic 7, you can actually see the Mastcam Z's high bay JPL. So there, you can see this is the head of Perseverance, the big kind of circle at the top. That's actually a port for a laser. That's for the SuperCam laser instrument, which does Raman spectroscopy and laser-induced breakdown spectroscopy. So basically zapping the rocks to see what they're made of. And then below that, the two big rectangles, that's the Mastcam Z's, the two eyes. And the reason we have two is so that we can actually do stereo imaging. Just like, you have depth perception with your eyes because you have two, the Mastcam Z's are able to give us depth perception with the rovers. We can actually make things like 3D maps.
Very cool. Well, I think it's time to go back to Sarah for another question from our live audience. Sarah, what do you got?
Sure. So Doggo on YouTube is wondering about how do you prevent biological pollution, or maybe Doggo means contamination, from the rover on Mars. I hear there's some sort of field called Planetary Protection. Can you speak about that at all?
Yeah, so planetary protection is something NASA takes very seriously. So what does that mean? Well, it means we want to protect all of the planets. That means both Earth and Mars from each other. And so that means we want to make sure that we don't bring anything dangerous back here to Earth. So, when we bring samples back, even from places like the moon, where we don't expect there to be much life, or comets, we make sure everything is quarantined, that it's, if we can, we sterilize it. So when we bring these samples back from Mars, one of the first things we have to do is make sure that they're not inhabited with modern life. And that obviously will be interesting for science, but also really important for making sure we protect our planet. But it goes the other way too. We want to make sure we protect Mars from all of the bugs, microbes and et cetera, crawling around on Earth. And so one of the things we try to do is make sure the rover itself is not quite sterile, basically, but as clean as we can get it while not damaging the instruments. So every single piece of hardware on the rover is carefully cleaned and documented, as it's taken apart and put back together, so that we try to bring as few bugs with us as possible to Mars. Partly to protect the ecosystem, we want to make sure we don't, overpower anything that's living there today, because we don't know, right? There might be little bugs living either in the subsurface or, near the polar caps or something like that on Mars. We're not sure. But also so that, if we go there and we see signs of life, we can tell that for sure it's not from Earth, right? That we know it's actually native Martian life. If we go and contaminate the whole planet, there's some ethics questions there, but also it just makes it a lot harder for us to tell what's going on. So that's an actual office that exists at NASA. We have an officer of planetary protection, and they try to make sure that we do the right thing.
Yet another cool job title at NASA, Planetary Protection Officer, among many cool job titles. Mars Rover scientist is super cool. So great question. Thank you. You were involved, though, Briony, in the selection of the landing site as one of the science team members of Jezero Crater. Tell us about that process. What was that like?
Yeah, so how do you pick the one place on Mars that you're going to collect maybe the only samples you ever get back from the planet? It's a tough question, right? If you had to pick one place on Earth to pick, a bunch of rock samples to tell you about the entire geologic history of the Earth, where would you go? Well, that's really hard. So this was a hard question. So, NASA likes to be as open as possible. And so the way this was done was that NASA put out an open call to the whole science community, and really anybody, to propose landing sites. And we started out with, I think, 60 different landing sites proposed on Mars for this mission. And gradually, over a period of about 5 years and big community meetings where we got together and argued about it, gradually narrowed it down to just 3 sites, and then eventually down to Jezero Crater. And so how do you choose a landing site like that? Well, for one thing, this is an astrobiology mission. So we want to try to go somewhere that has a good chance of preserving those ancient microbial biosignatures. So there's a couple different places you could go to do that, but we decided to go to Ancient Lake on Mars. Cool.
All right. Well, I mean, 60 down to 1. It must have been kind of a hard choice. But I wanted to ask you, in addition to just about some of the other things that you've done as a member of the science team and kind of making this mission what it is. In addition to the landing site, what are some of the other things that you and the other science team members have had to work on together along the way?
Yeah, so there's a couple of things. I mean, first off, we're still working on the landing site, so I can go into a little more detail on what we're actually going to see in the crater if you'd like to hear that. If you bring up graphic 8, you'll see a topographic map of Jezero Crater. And so Jezero, here you can see, so in this topographic map, blue is low and yellow is high. And so you can see the crater itself with all that blue indicating the floor of the crater and the rim surrounding it. And what's really unique about Jezero is you can see on the left this channel leading into the crater and another one leading out on the upper right. And those are actually ancient rivers that have been carved into the bedrock into the rim and actually created in Jezero Crater. So if you go to the next graphic 9, I'll see a nice map of the crater. And so what we're looking at here, so the grayscale background, that's just black and white imagery from our satellites in orbit, and the colors that are on top of that are colors from one of our spectrometers in orbit, the CRISM imaging spectrometer. And the colors are telling us about the composition of, and so if, for example, here green is indicating carbonate rocks, which is carbonate minerals, and red is telling us about olivine minerals. So olivine is one of the most common minerals in basalt and basaltic lava, whereas carbonate is a mineral that forms due to interacting with water. So you can already kind of get a sense of why we're excited about this location. The coolest thing in this image is this giant sort of fan-shaped feature, that's actually an ancient river delta on Mars. This is a place where that river that's coming in from the upper left flowed into the crater, created a lake, and then dumped all the sediment it was carrying out into this big river delta, just like the mouth of the Mississippi River or somewhere like that on Earth where you get these big deltas forming where rivers flow into lakes. That's what we're seeing here. And so you can actually see the landing site of the actual landing ellipse itself on top of that. And so hopefully somewhere around the middle of that circle, either on the delta or just right next to it. So this landing site, it's exciting because we have really clear evidence of this ancient lake exists, that we had persistent liquid water for a long enough time to create this ancient delta, to have water flow into the crater, create a lake, and then overflow out the other side to create that outflow channel we saw. And not only that, we see lots of cool mineralogical evidence for water here too. So those green rocks you can see in this color image, those are the carbonates. So carbonates form in water. And in this case, we think that some of the carbonates here, in particular that kind of green ring behind the delta, might have actually formed at the shores of this ancient lake. And that's really exciting because that's exactly the kind of place you would go to look for microbial biosignatures in a lake on Earth. In fact, there are plenty of places where in this kind of lake that's making carbonate, kind of, imagine kind of white carbonate sand on the edge of the lake, we see microbial mats growing all along the lakeshore, creating stromatolites, like we saw in the biosignatures graphic, sort of these rocks that are created from layers and layers and layers of microbes trapping the minerals, in this case, carbonates. So that's kind of what we're hoping we're going to find. We're hoping that we'll be able to study the carbonates that are perhaps formed on the shore of an ancient lake. We're hoping we'll be able to study the muds at the bottom of this ancient delta. The muds at the bottom of the ancient delta are also great for trapping organics and other biosignatures. And so between the minerals and the delta and the whole kind of geology of this site, we think it's one of the best places on Mars to go look for microbial biosignatures. So we've been doing a lot of work on the team to try to understand how we're going to explore this site. So we bring up graphic 11. You can see one idea that we were just about a year ago for what a traverse through this landing site might look like. So, of course, we don't know where we're going to land. So we have kind of two ideas if we land on the left side or the right side of the crater. What are some of the cool places we're going to be able to go explore and in particular get samples from for eventual Mars sample return? So we're hoping to explore the delta, sort of all the different parts of the delta. We see evidence for river channels and, muds and all kinds of different environments that used to exist along this ancient lakeshore, and eventually up into the crater rim as well, where we see signs of ancient hydrothermal systems that could have also helped preserve signs of life in those sort of warm, habitable environments. The other cool thing we've been doing on the team is trying to learn how to do operations with this rover. So how do we actually run the rover every day as a team? So if you go to graphic 12, you can see an example of a simulated rover mission out in the desert of Utah. So one of the ways that we sort of practice running a rover is we actually create a fake rover of people and instruments that run around in the desert and take data for us, and then send it back to the team who treats it like data from Mars and sort of puts together plans, science plans, engineering plans for investigating the site and looking for biosignatures at, what we call a Mars analog site on Earth. So a site that has characteristics that are similar to Mars in some way. In this case, this was also an ancient lake muds, ancient lake deposits that we're looking at here in this image that we were pretending to explore with our people-powered rover.
Very cool. I mean, you guys, and so clearly there's a group building the rover, but there's another group of people figuring out what to do with it. And where to send it and how to operate it. So it's a really exciting time, and I think that's about all the time we have for talking with you right now, Briony. But we really want to wish you and your science colleagues on the mission the best for launch, landing, and roving on Mars. And thanks for being here with us. All right. So, and I think there's a little bit of a lag. Thank you to everybody for hanging in there with us. But I was, her connection stayed right with us, so we got to hear from her the whole time. So, hey, that's a win. Well, so earlier I mentioned the engineering side of making a Mars rover, which involves a lot of testing. And before we meet our second speaker, we have a short video that shows a behind-the-scenes peek at the building and testing of the Mars 2020 rover Perseverance. Take a look. One of the things I love about that video is that you get a real sense of the human scale of the mission, and not only the physical size of the rover, which is, it's a big piece of machinery, but a feel for all the hardworking humans who are behind the effort to put it on Mars. And as part of that effort, we have these very special places at NASA-JPL that we call testbeds. And our next speaker is one of the humans who's helping to get Perseverance ready for its mission, and a couple of these test beds are his responsibility. So Armen Toorian is a mechanical engineer at JPL, and he serves as the lead for what we call the system test bed for the Mars 2020 mission. Hey, Armen.
Hi, Preston.
Well, tell us about your job at JPL. What do you do?
Yeah, so I'm the testbed lead for the Mars 2020 system testbed, and that's a very special place where we get to test everything from low-level ones and zeros moving around on our computer all the way up to really complicated behaviors like, is the rover able to intelligently navigate on the surface of Mars, or are we going to be able to land on the surface, and everything in between. So it's a really special lab with a lot of exciting hardware and testing that we do to cover all the different gamut of things we need to prove to be able to pull off a mission like this.
Yeah, it's incredibly, just mind-numbingly, mind-bendingly, I should say, complex stuff. But you are not a rover newbie. You worked on Curiosity as well, right? Or maybe still do.
That's right. No, I did. I worked on the Curiosity mission. First, I was working as a mechanical engineer, working on the actuators that drive the wheels and the robotic arm and all of those things. And then I worked in the test bed on the entry, descent, landing system. And now I'm running the lab where we're doing most of that testing.
All right. Well, I asked a similar question to Briony earlier, but I want to ask you as well. How does one get to be an engineer who tests robots that fly to Mars? How do you come to have this kind of job?
So I'm a mechanical engineer, and also I have a degree in mechanical engineering and aerospace engineering, and I've loved robots and space ever since I was a little kid. And I knew from very early on that I wanted to do something with both of those. There aren't that many jobs where you get to do that, and so JPL was kind of a natural fit for me. When I was in school, I worked on these little things called CubeSats, which are tiny little satellites. And I made a lot of connections that way. And I did an internship here at NASA-JPL, fell in love, and after I graduated, I applied.
Cool. Now, what is a test bed? What do we mean by that at JPL specifically, and what are they used for?
So test beds are really common in the engineering field. What it means is it's a place where you can test something that you're building. And these go anywhere from really low-level things like computers or motors, all the way up to what we call the system test beds, which is a pretty unique thing that we do at JPL, where we have basically all of the hardware, all of the equipment, and all the parts that would go into the rover and the spacecraft, all connected together, and we test them all as one venue, one test bed. And so we can do things where we have things that interact together. There's about 50 computers on the Perseverance rover. They all have to talk to each other. They all have to communicate. That's really complicated, and it takes a lot of work to prove that all of that is going to work properly. And so those are the types of things that we do in these system test beds.
Okay, it sounds like a very busy place. Why don't we go to Sarah for our first question from our live audience for you. Sarah, what do you got for Armen?
Sure. Well, I'm so glad that you asked Armen how it is that he became a mechanical engineer at JPL, because we had a question related to that. Alan on Facebook wanted to know if entry-level mechanical engineers are able to work on some of these missions. And I think I can answer that. Yes, entry-level people can do this important work, and also lots of interns, and JPL interns have had significant roles on our missions. However, the question I do want to ask Armen is from Rocky on YouTube. He's wondering about the wheels, how the wheels of Perseverance were redesigned, and how will these wheels resist some of the wear and tear issues that the Curiosity rover faced in Gale Crater?
That's a great question. So one of the test beds is something we call the vehicle system test bed, and that's where we assemble basically, as Preston likes to call it, a stunt double of the real rover. And it is a complete rover, basically exactly what we're going to be flying, but it's something that stays here on Earth and we can test with it. And one of the places we do this testing is called the Mars Yard. And if you bring up graphic 22, you can see a picture of that. This is basically a big lot we have on the JPL campus. It's like a playground for Mars rovers. We have all sorts of dirt that we can push around with tractors, make hills and of different grades and different materials. We have rocks that we can place as obstacles and for the rover to navigate around. And we do a lot of our testing here. And one of the things we found with the Curiosity rover is the wheels are designed to be really lightweight and strong. But we definitely underestimated the sharpness and the hardness of the rocks on the surface at some spots. And so we started getting holes in these rocks like Swiss cheese after a while. And, you know, Curiosity's been on Mars for a long time now. And so the wheels still work. They work great, but they are starting to get worn out. So there was a big redesign effort that was done for the Perseverance mission. And one of the things we use, other than trying a bunch of different tread patterns and thicknesses and materials, if you pull up picture 17, we have this rover that's also a test bed, not a system test bed, but this one's called the Scarecrow. And what this is used for is practicing driving around, including understanding the wear on the wheels. And the reason it looks like this, and the reason we call it the Scarecrow, is because it has no brain. But it is not the complicated VSTB that I'm talking about that we're currently building. It's a much simpler rover, but it behaves like what the real rover will on Mars. So gravity is different on Earth versus on Mars. It's about 3/8 of what it is on Earth. Everything's much lighter there. So if we drove around our VSTB in this Mars Yard, it's not really going to perform the same way as the real rover will. This is much lighter. The mobility system is stiffer and overbuilt, so it acts a lot more like the real rover will on Mars. And so this is some of the testing that we've done to end up with the wheel design that we have for this mission.
I've been here for years, and I still think it's super cool that we have a place called the Mars Yard. It's just so neat. And just to clarify, I think you said it, but VSTB stands for, is it Vehicle System Test Bed?
That's right.
Okay. So that's one important test bed, but there are several others at NASA-JPL for the work that you're involved in, right?
That's correct. We have a couple other test beds that we use for all of the other type of testing. So whereas the vehicle system testbed focuses on things like driving and eventually on drilling core samples and all of those types of surface related things, testing out instruments, we have another testbed called the mission system testbed that's much more focused on getting to Mars. So we have all of the hardware from the computers to the power assemblies and the sensors that we're going to use to navigate to Mars and then pull off the landing on Mars. And the interesting thing there is in addition to having all of that hardware, we also have all of these, what we call simulation support equipment. So that hardware, which is all sitting on a bench, is not very useful if your star scanner is pointed at a wall and your cameras are pointed at a wall, and you're measuring the gravity of Earth instead of what you're measuring as you're entering the atmosphere. So we have all of these simulations running that pretend to be those environments, and all of those simulations are connected to the hardware. So we can do things like do trial runs of entry, descent, landing, where we have a gravity model and an atmosphere model and all of these things that are keeping track of the theoretical position of this spacecraft as it's coming into the atmosphere, and then feeding that information back into the sensors. So the star scanner will actually see the stars that we think it will see when it's on its way there, or the landing radar will actually get radio waves as if it's seeing the surface of Mars, but really it's just coming out of a rack of computers. And so not only can we test the computers that are enabling all of this to happen, but we're also testing those computers talking to the sensors that are going to be enabling this mission. And so that's what makes these system test beds very special, is that we have everything there, and we have all of these simulations that let us make the hardware pretend like it's at any point in the mission, and we do hundreds and thousands of different tests and different varieties of iterations of those tests to make sure we understand how it's going to behave.
And can I just poke at that a little bit more? I thought it was, when we first talked about your work a few weeks ago, I thought it was fascinating that you're able to use these systems as sort of like flight simulators, Mars Rover edition, for the team as well, right? You can do simulations for your team and the operations folks in how they're going to operate the mission, but you can also do simulations for them to kind of run the team through their paces, right?
Sure, absolutely. As we heard in Briony's section, there's a lot of planning that happens to get the team ready for these missions. It's just a really complicated machine, and learning how to operate it and planning out what it's going to do day to day is very complicated. So one of the things we do with these test beds is we have the operations team that's in the building they're going to be in when they're running the mission. Like, for example, launch, we're preparing for coming up soon, and landing and other key activities. And we use the test beds to simulate the real spacecraft. So that test bed, the ops team is flying that test bed instead of the real thing. From their point of view, it looks very similar. In fact, in some ways, it looks identical. And so we can do things like practice their decision-making ability. We can do things like practice timing of different events that are going to happen, sending commands and getting telemetry back. And we even do off-nominal operational readiness tests where we have a whole team that's just creating problems for the ops team to solve. They don't know what they are, and we have to make it seem like something went wrong, and they have to figure out how to fix it. So it's a very valuable resource for us.
Very cool. So Sarah, I think we have another question from our live audience for Armen. Why don't you go ahead?
Sure. Manish on YouTube is wondering what the biggest challenges are to designing a vehicle that can function on a foreign planet. So maybe you can speak to the conditions on Mars that these rovers have to face. Sure.
There are a lot of different challenges, and every planet in the solar system has its own unique set of challenges. So what I'm saying will apply to Mars, but there's a whole other set of challenges for other missions that are going to moons of Jupiter and other places in the solar system. But some things are universal. Obviously, you don't have air, and even on the surface of Mars, we only have an atmosphere that's 1% as thick as what we have on Earth. So there's almost no air. You don't really think about it, but air moves a lot of heat, and so getting heat out of your electronics and out of your computers can be trickier. So we have pumps that actually pump fluid through the rover to cool it down, and things like that. Also, the dust on Mars is very fine. It gets in everything. So all our gearboxes and motors and all those things that need to move and do all these complicated activities need to be designed to be able to withstand that. And along with that, temperature. Mars gets really, really cold and really, really hot too. none of us would survive even a minute on the surface. So we have to design all of this hardware to be able to work. Things like lubricants, like the oil you put in your car, would freeze at night on Mars. And so we have to develop special lubricants to use in the gearboxes. So there's all these unique challenges. Radiation, another one of them. Your cell phone would last maybe a day up there. We have to design all these computers to withstand radiation. So there are a lot of unique challenges to designing something that works in space or works on another planet. But I think that's one of the funnest parts of being an engineer working in this field.
And Sarah, you had a follow-up question to go with that?
Yeah, well, it wasn't exactly a follow-up question, but it's a question I've heard a lot before, and I thought perhaps Armen could answer it. It's a common one. So it's High Flyer on YouTube is wondering how fast the Perseverance Rover will be able to move on Mars.
So that's a really good question. And if you, when things get back to normal, if you come and visit JPL on one of the tours, you'll see, you might see this rover driving around in the Mars yard, our test rover. And as you notice in some of these videos, everything is sped up. So everything is done really slowly. I think on Mars Science Lab, I'm reaching back, so if I get this wrong, don't hold it against me. But I think we were driving about 100 feet or so a day, and I think we're expecting to double that. It doesn't seem like a lot, but you have to factor in that the rover has to do all this autonomously, meaning we have no intervention. It can take between 14 minutes to half an hour just to get a signal to Mars, and then the same amount of time to come back. So we can't drive this thing like a remote control car. It has to take pictures of its surroundings. It has to process those images and create 3D maps of where all the hazards are, all the rocks, all the cliffs, all of that stuff. It has to decide what the best path forward is, and then it has to drive and stop and do that all over again. So to improve the driving performance, one of the things we did was add a whole nother computer, which is called the Vision Compute Element. It's basically a really powerful graphics card. It's going to process those images for us, and we'll be able to drive much, much faster than, or cover much more distance than we did on the Curiosity mission.
Now, Armen,
the rover will get a speeding ticket?
Not likely, not by our standards. But you know, we don't have to do things quickly either. We don't really get a chance to go and fix stuff if we get it wrong. So we get to command this thing once a day usually, and we get telemetry back once a day. And so we have plenty of time to do things nice and slow. Patience is a virtue.
All right, let's not get any speeding tickets on Mars. So Armen, you also told me about a thing that you guys do called shadowing, supporting the operations team, right? Can you tell us what that is?
Sure. Shadowing, what we refer to as mirroring or following along with what the real spacecraft is doing. We're getting ready to do that for launch in a few weeks here, or in about a month here. And so the idea there is that the twofold. One, we don't want any surprises with any commands we send to the spacecraft. We want to know that whatever we send, we've tried out in these test beds, and we know how the system's going to behave, and that everything's going to work the way we expect. So in one sense, we'll send commands here before we send them in real life, make sure they're doing what we think they should. And then on the other hand, we want to be ready to debug any problems that might come up. Let's say we get up in space and we don't see any stars, or we aren't in the right orientation exactly, or something is not working right, or a computer resets. We don't want to spend hours getting the test bed set up to be able to debug that problem. So we're following along in lockstep with the real mission, and as soon as something happens, we have a team ready to go that can just jump in and start working those anomalies.
I thought that was a particularly neat capability that you don't want to waste the time spinning up to get ready to figure out what to do. You're ready to go. Can you talk a little bit about some of the activities that you and your team have done in preparation for Mars 2020? You talked about some of the capabilities in these different test beds, but any specific things that you guys have done while you're preparing for the mission or testing it out?
Yeah, I think the two big ones right now are we're building the vehicle system test bed that I talked about. So that's going to be the stunt double of the rover, and we're having that come online later this year. That's a huge effort. Obviously, it's in many ways just as complicated as the real rover. We don't have to take the same cleanliness precautions and things like that, but it's still complicated. And then the operational readiness test I talked about, the anomalous one where we're throwing problems at the operations team, that was a big milestone to show that our infrastructure and our team and our management is all ready to react and take on any challenges that we might be faced with.
All right. I have no doubt that you guys will be ready to go. Sarah, we have time for a couple more audience questions. What do you got from Facebook and YouTube for us?
Sure. Let's see. We have this one from Ask NASA, I think. This is Astro Boy, who is wondering how long this Mars mission will last. Does it last until the rover collects all its samples and the data, or does it keep going? So either person can answer that one.
Sure, I can answer that if you'd like. So we like to keep our rovers going as long as possible. You know, the Opportunity rover was supposed to last 90 days, ended up lasting more than 11 years because of the amazing engineering work done at JPL. And so this rover, you know, actually both the Curiosity rover and the Perseverance rover do have sort of a limited life because they're actually nuclear powered. They run using a radiothermal generator, an RTG, basically with the radioactive decay of radioactive materials on the inside that drives a heat engine, which drives electricity for the rovers. And you know, those materials decay over time, and so eventually you actually do run out of energy. For the Curiosity rover, we're hoping it'll keep going for at least another 3 or 4 years, and we're hoping Perseverance will last just as long. So we're hoping we'll get, you know, we have to last a Mars year, but we're hoping we'll get a lot more of that from the rover. We're actually hoping we'll get to drive out of Jezero Crater onto the surrounding areas around, which there's lots of even better geology beyond the crater itself.
Yeah, we're not going to pull the plug on this thing. So as long as it's working, we plan to keep driving it.
All right, Sarah, you got another question for Armen.
Sure. I do. Benjamin on Facebook is asking, so which systems on the rover have redundancy to improve reliability? Sounds like kind of a good engineering question.
That is a great question. And if anyone's wondering what redundancy means, it just means backups. We have backups for almost everything. So we have, we have backup plans and backup hardware. We have 2 computers on the rover. They both are equally capable of doing the job. We only need one. So if we ever have a problem, we can swap that. We also have backups for a lot of the power hardware that will turn devices on and off and collect all sorts of information about the health of the rover, like temperatures and voltages and things like that. We have backups of some sensors, like we have an inertial measurement unit that can measure the compass in your iPhone or smartphone. It can measure the orientation of the rover, and so we have 2 of those. And a lot of the instruments have an A and a B side, so we can talk to them from either computer. So there's a lot of redundancy all over the system, and that's part of why these test campaigns are so thorough and take so much time and effort, because all that redundancy is complicated and the interactions are complicated, and we test all of it.
Yeah, Armen, I want to jump in and kind of wrap up with you by asking something I kind of missed earlier in our talk, which is that testing is a really important part of our culture at NASA-JPL. It's something that we do. We believe very strongly in testing. Why is it so important, and why is it such a big part of our work?
I think testing is really important for the aerospace field in general, especially anything leaving this planet, because it's not like other devices that are engineered to work here. You can't go and fix something if it breaks. You can't go and improve something if you didn't design it well enough. We have to plan for every contingency. We spend a lot of time understanding the environment that this rover has to operate in and the spacecraft has to operate in. And we do our best to design something that will work in that environment, but you don't really know until you test it. And the level of testing that we go through, I think, is extraordinary. And I think that's a big reason why we've been as successful as we have been, is because everything gets tested, like I said, from the lowest level down to like the parts, the microchips on the boards, all the way up to the entire rover and the spacecraft, all as one assembly. So testing is a huge part of the culture at JPL and NASA.
All right. Yeah, it's definitely something that's very important to the way we do our work. Well, that is about all the time we have to talk with you, Armen. Thank you so much for joining us, and really good luck to you and the team.
Thank you.
All right. Well, again, we want to thank Briony Horgan and Armen Toorian for being with us. We'll all be watching with a lot of excitement when that rocket lifts off next month. And thank you to Sarah Marcotte for sharing our audience questions. And of course, thank you, all of you, for watching and submitting those questions. Glad we could get to some of those. Now, again, if you are looking for resources from NASA regarding the Mars 2020 mission, you can go to mars.nasa.gov/Mars2020 and follow @NASA-Persevere on Facebook and Twitter. That's all for this month, but we hope you'll join us next month as we pivot our focus to Venus. We'll ask, is it Earth's evil twin, or maybe just misunderstood? You'll have to tune in to find out. So until then, stay safe, take care for now.